Okay, this is chapter 8.3, hypothesis tests in detail. So some key points about a one proportion hypothesis test. And keep in mind, chapter 9, we'll take a look at the hypothesis test for sample means. All right, so first bullet, it is a procedure for choosing between two hypotheses, where you have the null hypothesis and the alternative hypothesis. So we're choosing between those two hypotheses about the true value of a single population proportion. You calculate what's called a test statistic, so it's a z-score, and observed is just a reminder that that's something that comes from our sample. And we do that by taking our observed value minus the hypothesized value and dividing by the standard error. So this test statistic compares the sample proportion to the hypothesized population proportion. Again, hypothesized population proportion, what we have in the null hypothesis. So we're assuming that's true until we gather evidence to suggest otherwise. So keep in mind that large values of the test statistic tend to discredit the null hypothesis. So if you think of that sampling distribution for all those possible p-hats, this is saying large values of the test statistic. So large values are going to be in the tails. They're going to be extreme. Those tend to discredit the null hypothesis because this is what would result if HO is true. And if HO is true, these in the tails are rare or unlikely to be seen. All right, third bullet, the standard error, SE for short, is the null hypothesized value of P, that's why we have the subscript of 0, times 1 minus the null hypothesized value of P over N. So it looks just like the standard error we calculated in chapter 7. The only difference, again, is the subscript of 0, and that's really just to remind us to go back to our null hypothesized value. All right, fourth bullet gives us a way of making a decision about the population parameter based on our estimate from a sample. And keep in mind, anything from a sample has some uncertainty attached to it. So we're doing this while knowing the probability that we will incorrectly reject the null hypothesis. That probability is alpha. All right, next bullet. This test and procedure only works if the sample size is large enough and the sample is randomly selected. So remember, we're checking conditions 1 through 3, like we did back in chapter 7. All right, and last bullet, small p-values indicate an extreme test statistic. An extreme test statistic means something unusual or unexpected has happened. So those p-values, think of that as the area shaded in above. So this area is your p-value. So the smaller the p-value, again, the more extreme that test statistic. And again, that's all based on the assumption that the null hypothesis is true. So think of this as your surprise factor. How surprised are you at the result you saw in your sample? All right, below we have a diagram which is from page 373 of your text and illustrates this last point using a sample of 20 coin tosses to test whether a coin is fair. So a hypothesis test to test whether a coin is fair would probably have the null hypothesis with the proportion equal to 1/2 or 0.5, and an alternative hypothesis with p not equal to 0.5. So again, note they're just saying whether the coin is fair or not. So not saying they think it's weighted more heavily to one side, they just think it's unfair. All right, so with that in mind, let's assume that they're using a p-value. Oops. Let me erase that. Let's assume they're using an alpha equal to 0.05. Okay, so if we get extreme results, we're going to reject the null hypothesis. So in this first example, they flipped the coin 20 times and had 4 heads. And they calculated their test statistic. They got z equal to negative 2.6833. And according to our standard normal distribution chart, that has a probability of happening of 0.0073. So that's the area here in this tail and the corresponding area on the right-hand side. And it's so small that we actually can't see it. So that indicates an extreme value. And notice that that p-value is less than alpha, so we would reject the null hypothesis. This means we have an extreme enough example or case in our sample that it suggests the coin is not fair. In other words, getting only 4 out of 20 tosses landing heads, although it can happen, it's so unlikely that another explanation might be more likely. And again, that's that the coin is not fair. All right, so if we look at the second one, all right, so we'll just move to the right. They repeated this. They got 5 out of 20 heads. So here's the test statistic that goes with that. And they just calculated its z-score. And here's the p-value. So remember, that's the area in this tail and in this tail combined. So that's a little bit bigger. It's not quite as extreme as before. But notice that it's still less than alpha equal to 0.05. So we're still saying that's extreme enough that we would have some doubts about that coin. And it would lead us to conclude that this alternative hypothesis is the more likely explanation. All right, let's move on to the third one. Okay, in this case, they got 6 out of 20 heads. So this is the test statistic that goes with it, or its z-score. And using that standard normal distribution, this is the p-value they came up with. Remember, that's doubling the area you get from your chart. And that is the total of these two areas shaded in. And notice it's a little bit more area, so it's not as an extreme result. And since it's not less than alpha, in fact, it's bigger than alpha, we're saying we don't have enough evidence to reject the null hypothesis. In other words, that test result would happen often enough that we would assume the coin is still fair. And we don't have enough evidence to say the coin is not fair. All right, let's do another one here. Somebody else flips the coin 20 times, gets 7 heads. Here's the test statistic that goes with it. And when they calculate the area to the left of it and double it, because again, both tails, both value, or this type of test statistic in both tails, we need to account for both of those. That's a pretty large area. And just like before, it's greater than alpha, so we would not reject the null hypothesis. And that's a little bit messy. Let me see if I can make that a little bit better. Oops. Oh, I guess they're all tied together, so I can't erase that. So let me write it here. Okay. All right, so if we move on, notice here that we get 8 out of 20 heads, so not very extreme. We've got a lot of area on both tails, so our p-value is getting larger. Moving to the right, 9 out of 20 heads. We probably would expect 10, give or take a couple. So large area. This is telling us that's not an extreme result. So we wouldn't have any evidence to suggest that rejecting the null hypothesis is necessary. Look at what happens when you get exactly 10 out of 20 heads, which is what we would expect if the null hypothesis were true. P-value is as big as it can be. Includes the entire area underneath that distribution. And that's because our z-score would be 0. This would be our test statistic. And here, 11 out of 20 heads, very similar to 9 out of 20 heads, it's just a little over instead of a little under. So notice the z-score, or test statistic, is just the opposite of the previous one. So it has the same p-value as before. And then our last example here, 12 out of 20 heads, again, not as extreme, or not extreme enough to reject the null. It's a fairly large p-value, that's the combined areas of these two places. So not extreme enough, not far enough out in the tails to reject the null hypothesis. So we would fail to reject the null hypothesis in that case. Okay, so number 2, what do we do if it's not possible to collect a random sample? Medical researchers often cannot collect a random sample of people with a medical condition that they wish to study. They instead must rely on recruiting patients who come into hospitals. This type of convenient sample can be problematic for the statistical techniques we just learned, so sometimes we have to assume that the sample is random and/or representative of the population, and then use caution when interpreting the results. If the medical study is a randomized controlled experiment, then the researchers may conclude that the treatment is effective for those people in their study, and then others may try to replicate the results with further studies. All right, number 3, what are the 2 types of mistakes or errors that can be made, and how do we balance these? So remember that mistake number 1, or a type 1 error, is that you reject the null hypothesis when it's true. So notation, this is the probability that you reject the null hypothesis, we're going to use HO for short, given that HO was true. So for instance, you conclude the die is not fair when in actuality it is. And that probability is alpha, that's your significance level. So the probability of this happening is indicated by your significance level. In fact, the smaller you set this probability, or that significance level, it means the higher the probability of making the mistake number 2. So it might be tempting to make this really tiny, set alpha equal to a really small value and minimize the chance of making that mistake. But there's going to be a trade-off. The smaller that is, the smaller that probability is, the more likely that we make the other type of mistake. And remember, mistake number 2 is the probability that you fail to reject the null hypothesis, given that the null hypothesis, or HO, is false. So mistake number 2, again, you fail to reject the null hypothesis when it's wrong. Question then is, which mistake is worse? Well, it depends on the study. Okay, I just want to make one more note here before I move on. And keep in mind that we call this, or most textbooks refer to this as a type 1 error, and this as a type 2 error. And the type 2 error, also keep in mind, we can't calculate the probability of that right now. We can conclude that it's going to be higher, that probability will get higher, the smaller we make alpha, our significance level. All right, so for number 4, for each of the following, we're going to state the null and alternative hypotheses, and then describe each of the 2 possible mistakes. So what would happen if we use the significance level of alpha? So in other words, if we let alpha equal to 0, significance level of 0, or alpha equal to 0. All right, so in example 1, person suspects the die used at a casino is biased. She decides to test this by rolling the die 100 times and recording the number of 6s. Well, our null hypothesis, again, that status quo, is that it's a fair die. So we'll say the die is fair. The alternative then, she didn't specify direction, just that it's unfair. So we're going to use P naught equal to 1/6. And in words, this is the die is unfair. All right, well, mistake number 1 means that you can conclude the die is not fair when the die is actually fair. Mistake number 2, you're going to conclude the die is fair when the die is actually not fair. So again, the question is, which mistake is worse? And on this last, or the one we just did, if alpha equals 0, so we'll just say if alpha is 0, you would end up concluding all die is fair, or all dice are fair, even if they aren't. So remember, if alpha is 0, I'm just going to draw a line up here, means the probability that you reject HO, and that when HO is true, so you're rejecting the null, and you're concluding all dice are fair. So in other words, if this probability is 0, means there's no chance you're going to reject the null hypothesis. And rejecting the null hypothesis is saying that you have evidence to suggest the dice are not fair. All right, on the next one, example number 2, a person is on trial for a specific crime. The prosecutor collects evidence for the case. So we're not going to use symbols for this one. So we're not talking about a proportion. We're just going to say the null hypothesis is that the person is innocent. Again, the way our justice system works. And the alternative is that the person is guilty, or we can say the person is not innocent. So again, that's another way of just saying guilty. Okay, so mistake number 1, we would conclude the person is guilty when the person is actually innocent. In type 2, or mistake number 2, we would conclude the person is innocent when the person is guilty. All right, so over here on the side, let's think about what would happen if alpha was 0. So that means we wouldn't reject the null. All right, that means that we would conclude everyone is innocent. So we never mistakenly conclude that someone's guilty, but it also means we would never send anyone to jail. We would not catch the ones that are actually not innocent. All right, and the last one, example number 3, a new medical procedure is being tested in the fight against lung cancer. The doctor suspects that this medical procedure will help improve survival rates. So we weren't given a number, so we'll just say that P is the current survival rate in the status quo. So whatever that number is would be our null hypothesized proportion. And in other words, that means the medical procedure doesn't improve survival rates. And then your alternative is that your proportion is actually going to be greater than the current survival rate. So this one specifies a direction. Oops. And that means that the medical procedure is improving your survival rate. All right, so your 2 mistakes. Mistake number 1, you would conclude the medical procedure works. When the procedure doesn't. And mistake number 2, we would conclude the procedure doesn't work. When it actually does. So when the procedure actually does work. And again, what we want to do is think about what would happen if we made alpha equal to 0, because we were hoping to minimize that type 1 mistake. So if we said alpha equal to 0, we would conclude no medical procedure works. Or we would never conclude that a medical procedure works. Okay, statistically significant findings do not necessarily mean that the results are useful. Statistically significant results tell us that our sample results are so extreme, again, when compared to what we would expect to happen if the null hypothesis is true, that it cannot be convincingly explained by chance. So keep in mind that when you state your conclusion to a hypothesis test, you're not proving that the population proportion P is or is not equal to a particular value. That's just too strong a word. So if something is proved, then it is absolutely and without any doubt true. So absolutely meaning 100% absolutely certain. However, you can't be absolutely certain about your results since they come from a random sample, and estimates from a random sample are uncertain. That is why we limit ourselves to one of the following conclusions. Again, we either reject the null hypothesis or we don't reject the null hypothesis. And we don't want to say we accept the null hypothesis. And we don't want to say we've proved anything. Okay, so we're choosing the conclusion that seems most likely given our sample data. So instead of saying something like proved, use words like demonstrated or showed. All right, number 7. Let's revisit the first hypothesis test we did about whether or not a die was fair. Let's say I rolled the die 60 times and recorded 56s. So this is a different sample, so this is just hypothetically. The following are the results of a confidence interval and a hypothesis test done in StatCrunch. So before we get to those, keep in mind that our null hypothesis was that the die was fair, and our alternative hypothesis was that it was unfair. Okay, and if we look, our p hat is 50 out of 60. If you grab a calculator, you'll see that that is the sample proportion given here and also here. All right, so they're similar in terms of the hypothesis test and your confidence interval, that you're going to have the same p hat. So this is our confidence interval results here. This is our hypothesis test results here. Your confidence interval has a standard error calculated here. So that was calculated by doing p hat times 1 minus p hat over 60. So here's your standard error. And then your confidence interval, here's the lower limit and the upper limit. So this is p hat minus your margin of error, and this is p hat plus your margin of error. Right, so notice in that confidence interval that this doesn't include our null hypothesized value of 1/6. And remember, that's about 0.17. So your confidence interval is suggesting that 1/6 is not a likely value or a plausible value for p. I mean, if we look at our hypothesis test, notice that our standard error is very similar, or actually it's the same in this case, because our null hypothesized value, let's see, we did 1/6 times 1 minus 1/6 over 60. And 1/6 and 5/6, if you check, this actually reduces to 5/6, which is why we're seeing the same standard error here as above. All right, the test statistic, and that's z equal to what you observed in your sample minus the hypothesized value over your standard error. And note that's very extreme. It's a very large test statistic. And remember, large test statistics or extreme test statistics have very tiny p-values. So that's the last piece here. Notice on the right in this output, that p-value, they didn't give you a number. They just said it's less than 0.0001, so less than 0.01%. And that's definitely smaller than what we set alpha to up above. We didn't set an alpha, but typically if we use alpha equal to 0.05, we would find that that's smaller than 0.05. So that would lead us to reject the null hypothesis in favor of the alternative, which means that we have evidence to suggest the die is not fair. So these two results are somewhat complementary in that case. Again, the confidence interval here is suggesting that a proportion equal to 1/6 is not a plausible value for our die. And our our hypothesis test is doing the same thing, suggesting that p equal to 1/6 is not really a plausible value. So how are these results related? Again, both results provide evidence, not proving, but again, providing evidence that p does not equal 1/6. Okay. All right, so remember that confidence intervals are used to answer the question, what is the value of this parameter? And a hypothesis test is used to answer the question, are the data consistent with the parameter being one particular value, or might the parameter be something else? Okay, keep in mind that confidence intervals and hypothesis tests, if it's two-sided, so remember this was a two-sided test, so hypothesis tests with two-sided alternatives are closely related. In fact, your confidence level, if you look here, is 95%. That's equal to 1 minus alpha. I mean, that's your significance level. So a confidence interval provides a range of plausible values for p, your proportion, and you should not be surprised if p turns out to be one of the values in your confidence interval. So we wouldn't be surprised if the true proportion of 6's, when you roll that die, is somewhere in here. We would be surprised if we get a p that's not in there, or if p is actually a value not in that interval. So keep in mind that we may have a different standard error for these two. This and this may be a little bit different. In this case, they were the same because our test statistic, our observed sample result, 50 over 60, is the same as 5 over 6 if we reduce that. So because they may not be the same, there's going to be some rare cases where you can reach different conclusions with the confidence interval as you would with a hypothesis test.